In this video, we're going to look at using ground distances and true bearings as described in the BLM Manual of Survey Instruction. Really what we're talking about in this example that I'm going to show you here today is we're working east of the central meridian on a state plane projection. Now, it's the state plane projection that relates geodetic positions, latitude and longitudes, to a coordinate position for us. And in the example I've shown you here, we can see that I've got a state plane grid underneath. East of the central meridian, we see that if I'm working on an arc of latitude, I really am dealing with grid bearings that tend southwesterly instead of due west. And this arc of latitude, of course, represents a true west line anywhere on this grid. And we're going to talk about how Traverse PC basically relates these for us. Let's start by going up to the Tools menu and bringing up the survey information for this particular survey. We're using a coordinate reference system that's a state plane projection using NAD 83 for the continental U.S. That's our horizontal datum. We're in the Washington North Zone, and we've chosen the WGS 84 for our ellipse data here. So that's what sets up our state plane coordinates. Now I want to click on this project factor, and we can see that this project has specified project elevation of 1,500 feet. And really, according to the Survey Manual of Instruction, we want to pick an elevation for this project, and all of our measured distances are going to be assumed to be at this elevation. When Traverse PC gets an input of a distance at this elevation, it will reduce it to grid for the computations on the state plane coordinate. So what we want to tell Traverse PC then is that we want to use this elevation. And I do that by choosing the preference here that says geodetic distance at project elevation 1,500 feet per the PLSS, per the Public Land Survey System. That PLSS is a heads up for us. We're going to see that at different places in Traverse PC. It says this is the option you want to use if you're doing computations on the Public Land Survey System. I'm going to just expand this. And we can see that in addition to grid distances, we have distances that relate to the state plane coordinate system, and that's where that combined factor would come into play. And we also have geodetic options for the ellipsoid surface, or the one that we want, which is at the project elevation. The 2009 manual also refers to the fact that what if we've got some large elevation differences and we want to consider the elevation factor for each individual course. That's a more rigorous computation, but we can tell Traverse PC that that's what we want to do by choosing a geodetic distance at mean course elevation. So for now, let's stick with the project elevation of 1,500 feet. Let's also choose the preference we want for directions. And so in addition to a straight grid bearing, we can choose this option that says, I want a true bearing based on the mean course convergence. So Traverse PC is going to use the state plane relationship between geodetic positions and grid positions to compute the convergence for us. And we're actually going to use that convergence at the beginning and end of each line to generate a mean bearing and use those in our computations. So that's the option we want here. So let's jump in now and take a look at how we would handle this with a strict grid coordinate type of computation. And I'm going to open up a traverse here called East-West Grid Bearing. And let's bring up the format for this. And we can see that we're not using the preferences here for distance and direction that we selected for the survey. We've gone into this list and we've said, let's deal with strictly grid distances and strictly grid bearings. We're also going to set the units to 66, so we're going to be entering chains even though our survey is in feet. Let's take a look now at this traverse. We see that the column heading for the bearing says grid bearing, and the column heading for distances says grid distance. So what we've actually entered here are 5 miles due west of 80 chains and a grid bearing of 90 degrees west. What I want you to notice here is that our grid bearing is constant, but because we're relating these grid coordinates to geodetic positions, we notice that our latitude is not constant. And we expect that if we're just doing a straight grid bearing due west, we expect that the latitudes are going to have to change. And in fact, let's switch back over here to our map and take a look at this. In the drawing settings, I've actually told Traverse PC we're going to plot geodetic or grid distance and grid bearings. If I want to relate the units back to chains like I did in the Traverse view, I can. So what I'm actually plotting here are grid bearings due west. And we see in the text right below the line here that on a state plane grid, a westerly line of constant grid bearing draws straight. Okay? So I get the straight line I'm looking for, but my latitudes change. So I'm not on this constant arc of latitude that I'm interested in for the public land survey system. And we've put some drawing variables down here on the drawing also that tell us what drawing settings we currently have chosen. In this case, grid distance and grid bearing. So now let's go ahead and take a look at a second option. This is a line of constant latitude. So in this particular option, let's open up the Traverse for it. Here's an east-west constant latitude. We basically have the same position starting at the same point, but we've come in and entered a constant latitude for each one. Okay? And as I would expect, my grid bearings and distances are not the same. In other words, if I'm going to have a line of constant latitude on a state plane grid, I'm going to have changing grid bearings between each course as I go west. If we go back to our drawing earlier, we can see that as I start over here on the east side and move west, my convergence is changing based on this latitude of arc here, and so my grid bearing has to change. If you look at this line of sight line, this is really the grid bearing for this particular point on the latitudinal arc. But as I move across that latitudinal arc toward the central meridian, that convergence is going to change until it's ultimately 0. And if that's the only spot on the whole grid where my grid bearing is going to match my true bearing. Okay, so now let's jump back to our drawing we were working on here. And let's drop back into the traverse that we want. So here's our traverse of constant latitude. And we see that the bearings change just like we expect. Let's go ahead and close that out. Let's close out our other traverse also. And now let's look at a third option. I've got a drawing here called True East-West Line. And let's open up the traverse that is tagged for that. And I've created a drawing for each one of these traverses just so I could label them a little bit differently for you. Now let's take a look at what we entered in this traverse. Let's go to our traverse format, and we see that here we're using the preferences that we specified for the survey. So our distances are geodetic distance at project elevation of 1,500 feet, and our bearings are true bearings based on the mean course convergence. Let's OK that, and let's come back now and take a look at what we've actually entered here. If I were to highlight one of these distances of 80 chains, I want you to take a look at the status line at the bottom of the traverse view. When a distance is highlighted, it tells us that the units are in chains, and this is a distance at a project elevation of 1,500 feet. So this is a geodetic or a ground distance at the project elevation. Our grid distance would be different, probably less than this, depending on our grid factor. Okay? If I were to highlight a bearing, I see basically the same thing down here, that this true bearing is based on the mean course convergence. So it's telling me what kind of a bearing I'm actually dealing with. And because I've computed the forward positions or the foresights based on a true bearing, I expect my latitude to be constant. And in fact it is. So I'm actually getting a true line here, even though the grid bearing is tending west. So let's take a look at the drawing, and let's just kind of put all this together in the drawing itself here. So I've gone into the drawing settings, and I've said I actually want to plot geodetic distance at project elevation and true bearings, and let's set this back to a 66 so we plot our chains as well. And when I choose OK, Traverse PC labels those lines or annotates those lines for me with true bearing and distance just the way I would expect it to. Okay, so I'm getting just what I expect with this north 90 degrees west and 80 chains that matches the input that I gave it. And if we look at the text here, we see that on a state plane grid, a true west line actually drifts south, so the bearings are actually changing. And again, we put the variables in here that remind us that we're actually plotting a geodetic distance at project elevation and a true bearing based on the mean course convergence. So let's put a couple of things together here now. Let's bring up our traverse, and let's bring up a COGO option called random inverse. Let's just put in a couple of points, 201 to 202. And let's talk about the three places inside Traverse PC, or really any survey software, where we are accounting for this geodetic or ground distance and the true bearing. We've already been working inside of a traverse, and we actually told Traverse PC that everything we do in this traverse we want to be based on geodetic distance at project elevation and true bearings using the mean course convergence. So when we entered 80 chains, Traverse PC assumed that was 80 chains at ground elevation, and that the direction we gave it was 90 degrees true bearing, so along the latitudinal arc in this particular case. And we saw how we could switch from grid bearing and distance to true bearing and geodetic distance in the different traverses we looked at. We also looked at a drawing here, and we found out that in the drawing settings I can tell Traverse PC what kind of annotations I want to work with in this drawing. This particular drawing has the geodetic distances plotted along with the true bearings. So I'm actually plotting per the PLSS. The third option I wanted to show you was to bring up one of the dialog boxes, and I'm going to turn the show options on here. And we can see that once again even the COGO knows enough to work with grid distances or geodetic distances and grid bearings versus true bearings. I'm just real quickly going to switch this to a grid distance and to a grid bearing. And we can see that the information displayed in the COGO dialog box is now grid information, and I can just as easily switch it back so that we're using geodetic distances and true bearings, and just hide those options. And now I'm really inversing on the PLSS. So we find that we're basically going to see the same options for distance and direction in the traverses, in the drawings, in the COGO. And this is what allows us then to switch Traverse PC from a coordinate computation type of program to a geodetic type of program tailored specifically for the public land survey system.